Hello everybody! In this video I'll be deriving the derivatives of the inverse trig functions because those are the ones that I always forget, and also this video should really not be hard and require very little preparation because I'm doing some research, a little bit of nothing groundbreaking. I'm just doing a little bit of research in number theory, and I want to do a video on the fundamental group in algebraic topology, but I haven't uploaded in ages, sorry. So I thought I'd just do something quick and easy. And also, I haven't mentioned, because it's so comfortable I didn't even notice I was wearing it, but provides such great warmth. And the material, look at the, yeah, that's right. More merch, not for sale again. Yeah, okay, let's just do this. This is a good exercise for implicit differentiation, I guess. I don't see how else you'd do it. If you can tell me another way to do it, I'll be very impressed. But I'm pretty sure that you have to use implicit differentiation. So first of all, we'll do inverse sine of x. Okay, I always forget all of these, so I don't really know what the answers are. I just know that for the inverse secant and cosecant, I need an absolute value of x for some reason. But okay, I'll just trust myself. Okay, implicit differentiation. We let y equal inverse sine of x, so we want to find dy dx, okay? But remember, an important note is, we don't want our answer to be in terms of y, okay? So I'll show you what I mean. So this means that sine of y equals x by definition, and now positive cosine of y equals 1 because we differentiated both sides with respect to x, but we have to multiply by the derivative of the inside. The derivative of y with respect to x is dy dx. And now we've squeezed the dy dx out just like toothpaste. We've kind of extracted it somehow. And here's what I meant at the start. Now dividing both sides by cosine of y leaves us with dy dx equals 1 over cosine of y. But that's not going to give you any marks in a test because, that could really be anything. If I set y equal to certain values, certain functions, this could be really anything I want it to be. So we need to get something in terms of x, okay? Because this is just some constant in the x world, so basically we don't want this. We want cosine of y in terms of x. And the way to do this is, here we see that sine of y equals x, okay? So how do we get cosine in terms of sine? Well, we should always look at this identity. Sine squared y plus cosine squared y equals 1, okay? This is always so helpful if you want to get a sine from a cosine. Always just go back to this. So subtracting both sides by sine squared y leaves us with cosine squared y equals 1 minus sine squared y. And now taking the square root on both sides leaves us with cosine of y, not going to bother with the absolute value here, equals the square root of 1 minus sine squared y. Okay? So now this equals 1 over the square root of 1 minus sine squared y. And now squaring both sides on this side, this equals 1 over the square root of 1 minus x squared. And that's it. That's the actual answer, okay? Put that on your test. So I'm just going to write this down because I need space to write all 6 of them. Okay? That's the first one. And I'm pretty sure we can just do the exact same thing for inverse cosine. So let's just do this quickly. The derivative of inverse cosine of x equals, okay, so same thing, y equals sine inverse sine of x, which means that sine, why am I doing this? Cosine, gosh. Which means that cosine y equals x. Differentiating both sides with respect to x leaves us with negative sine y dy dx. Again, we've squeezed it out like toothpaste. Equals 1, which means that dy dx equals negative 1 over sine y. And using the same reasoning as before, this equals negative 1 over the square root of 1 minus cosine squared y, which equals negative 1 over the square root of 1 minus x squared. Squaring both sides here. And that's it. That's the answer. So, yeah. If you're wondering how I went from here to here, just use the identity that sine squared x plus cosine squared x equals 1. Subtract cosine squared x from both sides and take the square root. Same thing as we did before. Okay? Now we'll do the cotangent and inverse, inverse tangent and inverse cotangent in blue. So the derivative of inverse tangent of x. You guys should know this. This is the only one that I can remember because this actually comes up surprisingly often in integrals. And I think I had to use this in the integral of square root of tangent x. So yeah, but here's how you get it. Same reasoning. Y equals inverse tangent x. Therefore, we're trying to find dy dx. Tangent y equals x. Differentiating both sides leaves us with secant squared y dy dx equals 1. Dividing both sides by secant squared y leaves us with dy dx equals secant squared y is 1 plus tangent squared x. So that's how I'm going to write it. But tangent squared y, of course. And now squaring both sides, this equals 1 over 1 plus x squared. And that's the answer. Okay? Simple as that. Once you get the hang of this, these should all come naturally. Although you have to be careful with the secants, which you'll see why in a sec. But first let's do cotangent, inverse cotangent of x. Which, so let y equal inverse cotangent of x. Therefore cotangent y equals x. Therefore negative cosecant squared y dy dx is 1. Therefore dy dx equals negative 1 over cosecant squared y, which equals negative 1 over 1 plus cotangent squared y, which equals negative 1 over 1 plus x squared. Okay? So you just did the same thing as before, except with this is negative cosecant y, squared y. Yeah, okay. Yeah, that's it. Negative 1 over that. And here is where we have to be careful. Secant is a bit trickier, okay? Because there's not some nice identity we can use, like the sine squared x plus cosine squared x equals 1, because you'll see in a moment, let y equal inverse secant of x, therefore secant y equals x, therefore secant y tangent y dy dx equals 1. Okay? Now you see, now you see, I don't really know, there probably is some trig identity, there are so many, but I don't really know any trig identities which, like, secant y tangent y equals some other thing, like some constant or whatever. So I don't really know. So dy, I don't know. dy dx equals 1 over secant y tangent y. And our best hope is to plug in y. So, here we go. When we plug in y, which equals 1 over secant of inverse secant of x times tangent of inverse secant of x. Okay? So this is easy. Secant of inverse secant of x is just x, which means that secant of y equals x. Okay? So now let's draw a right angle triangle. Let's call this angle y. So if secant of y equals x, that's equal to x over 1. So now recall, what is secant? Secant is not adjacent over hypotenuse, that would be cosine. Did I just... Yeah. Adjacent over hypotenuse would be cosine. Yeah, I don't know. I'm dying today. Okay, but hypotenuse over adjacent, okay? Because it's just the reciprocal of cosine. So this is the hypotenuse, this is the adjacent. So now using Pythagoras' theorem, x squared equals 1 squared. Just call this side c. X squared equals 1 plus c squared. Square root. Why am I... Oh my goodness. X squared minus 1 equals c squared. Square root. I'm so bad. Equals c. Finally! Oh my god. Why am I so... This is the square root of x squared minus 1. Now we can find tangent of y, which is just opposite over hypotenuse, or square root of x squared minus 1. So this equals 1 over absolute value of x. Don't ask me why, I just know that you have to put the absolute value for some reason, times the square root of x squared minus 1. And that's how you do the derivative of inverse secant. Okay? Yeah, okay. And now the last one for today is the derivative of inverse cosecant x. Ooh. Interesting. So if we let y equal to inverse cosecant x, that means cosecant y equals x. And I've just forgotten the derivative of cosecant y. So we'll have to do it together. I'll just do the derivative of cosecant x, which is 1 over sine x. I'm just going to quickly do this using the chain rule. Quotient rule equals something over sine squared x, because we square the bottom. F prime times g just becomes 0 because the derivative of 1 is 0, minus g prime times f, or cosine x, which equals negative cosine x over sine x times 1 over sine x, which is negative cotangent x cosecant x. Okay, cool. Alright, so that means that negative cotangent y cosecant y dy dx equals 1. And now dividing both sides by this leaves us with dy dx equals negative 1 over cotangent y cosecant y Now using the same reasoning, we draw our right angle triangle. Cosecant of y is obviously just x, because when we plug in our y, blah, blah, blah. Let's call this angle y. So, cosecant is the reciprocal of sine, or hypotenuse over opposite. And if that's x, which is equal to x over 1, okay? Now, call this side b. To find out b, just use Pythagoras. X squared equals 1 plus b squared, which means that x squared plus 1 equals b squared, which means that taking the square root on both sides leaves us with x squared plus the square root of x squared plus 1 equals b. So we can put that in there, square root of x squared plus 1. Okay, and now we can easily find cotangent y by doing the reciprocal of tangent y. What's tangent? Opposite over that. So, opposite over adjacent. So what's cotangent? Adjacent over that. Yeah. I'm not sure why I got angry, but yeah, I did. Square root of x squared plus 1. Okay? Overall, this equals negative 1 over absolute value of x, don't ask me why, square root of x squared plus 1. And, crap, I missed the camera. Close enough. We're done. Ah, crap, no, we're not done. I have to write this in. Negative 1 over absolute value of x, square root of x squared plus 1. And now, we're done.